Wonderful. Thank you for having me.
Show the image. Yep, okay. Hello, everybody. We're going to be starting our session right now. This is going to be session number 4 for all of the accepted paper presentations. And the topic for this one is advances in NLP models and techniques. Right now, we're having this paper towards an implementation of rhetorical structure theory in discourse coherence modeling. And our presenter is Michael, and this is a long paper. Michael, please take away.
Thank you very much. So hello, my name's Michael Lambropoulos, and today I will be presenting work based off of my honours thesis compiled with the help of Professor Ishihara from the Australian National University. Apologies I couldn't join you all in person today, so thank you in advance for your attention. So, to provide a bit of understanding of motivation, due to recent advancements in NLP, such as the advent of attention-based transformer models, we've been able to achieve much higher quality text generation and problem-solving abilities, with additional improvements seen in tasks such as machine translation, language modeling, and sentiment analysis. Long-form generation, when I refer to the term long-form generation from here, I'll generally mean longer spans of generated text. However, there are some drawbacks, as we can observe over long enough spans, things like salient features are eventually lost and slight deviations from source material occur. So despite this improvement in text generation, this still shows a need for higher quality in longer spans of text. So we come to the question of how can we explain choices made in generation of long-form text, and how can we evaluate them? Well, evaluations exist, but they are not complete. So we have perplexity as an evaluation of the model itself, and most evaluations of text fall short as similarity comparisons or rearrangement-based evaluations, which operate under the assumption that there is a single ideal arrangement of text. As such, we need a more grounded method for evaluating long-form text, which could improve interpretability of generation tasks. Among the many human and automated methods of text evaluation, there are none that account for both structure and persistence of topics in long-form text. As such, we arrive at the theory of discourse coherence described by Jurafsky and Martin, which is a linguistic theory outlining a way to assess the coherence or fluency of a body of text. And there are two core principles underpinning discourse coherence, the first being local coherence, which is concerned with meanings of text in close proximity with one another and tracking important textual entities and salient features throughout these spans of text. Zooming out, we then have global coherence, which compares the structure of bodies of text. And as an example, we can look at certain discourses like scientific papers or some stories which follow a more or less formulaic layout with regards to information presentation and flow. As part of the discourse coherence framework, rhetorical structure theory is a way of representing textual discourse in order to help us provide an assessment on discourse coherence. This allows us to segment text into its core components or elementary discourse units, which exist as either nuclei or satellites. Nuclei being segments which are understandable on their own, and satellites typically being dependent on the nuclei. As such, EDUs ultimately have a linguistic justification, and for sake of understanding, they're typically smaller in span than sentences. To provide an example, we can see that parts of a sentence are designated as EDUs, and they are connected via a relational link. This can then be expanded to represent an entire body of text. To provide an example of global coherence, on a more abstract level, we can see how certain texts can be represented much more structurally and what these varying segments represent. So is this utilized in the literature? Well, to varying degrees. Local coherence is mainly used in discourse coherence assessment and modeling, or for out-of-domain tasks such as in scene or topic selection. To provide a brief history of the coherence modeling progression, we started out with the entity grid-based models, and from there a sentence reconstruction approach was adopted before much more recently the neural net approach to the problem. However, global coherence is not typically accounted for in the literature as a whole, leading us to ask what is the best way to assess or incorporate it. A recent publication by Liu et al. Incorporated a graphical approach to the problem using graph convolutional network architecture, mainly to compare structural similarities across documents. As such, the main body of this work seeks to serve as an extension of this approach to the problem. Here's just a brief explanation of how GCN architecture is used. We feed a graphical representation of text to the model and use it to ultimately provide some prediction, in this case, a coherence score. As a brief aside, I'll quickly speak on knowledge graphs with the motivating idea to represent data at an enormous scale using unique explanatory connections between nodes. And there is some importance in providing justification for implementing this at a linguistic level. So we can observe use of local and global discourse coherence in previous work, but currently no combination of the two. Why choose a graphical approach? Well, we choose one since it is a promising direction, allowing us to create textual representations with some semblance of structure or meaning. This can also reinforce the practice of treating textual analysis as a knowledge graph construction problem. The aim of this work then is to explore linguistic theory with computational techniques, and hopefully we can use the results to gain a better idea of the validity of discourse coherence theory and principles. So to discuss the methodology, we use different methods for constructing graph representations of the data, one with discourse coherence principles, and we then compare that to a baseline of a graph representation constructed with sentence similarities. We choose a graph attention network model, or GAT, because there are more options with regards to hyperparameter flexibility, with the intended potential for more thorough analysis of how to assess discourse coherence. To briefly discuss the dataset we used, the Grammarly Corpus of Discourse Coherence, or GCDC, contains 4 different datasets, with each dataset containing various types of discourse, and each part of the dataset has a label between 1 to 3 depending on how coherent the text was. And this has been used as a standard for discourse coherence modeling tasks since its creation. Here's just a quick example of what you may find in these datasets. So to discuss construction of the graph representations, we use feature extraction to represent the text as a series of nucleus satellite relations. We use pre-trained EDU segmentation and RST parsing models to then derive the final RST representation. And the ultimate product is 2 types of graphs at different levels of connectivity. Finally, we use this graph representation as input for our models. Here's just a brief explanation of the feature extraction process. Depending on whether or not we do similarity connections, we end up with 2 types of graphs with different levels of connectivity. With regards to model choice, we introduce a flexible implementation of a graph attention network with additional variable hyperparameters. We then compare this model to the baseline state-of-the-art GCN model, and we also performed an optimization search on the GAT hyperparameters before evaluating performance on the full dataset and conducting comparisons. Here's just a brief overview of how the GAT architecture works. So we apply a variable number of attention heads and layers to a graphical representation of the text, again, ultimately to obtain these coherence label predictions. So to discuss results, Ultimately, they were competitive but established no new state of the art. It was interesting to note that we saw a significant performance increase in historically what was the weakest data set. We also looked at the F1 score metrics and noticed a considerable improvement across all 4 datasets. The reason we emphasized this aspect of the study is due to the results in accuracy, as well as the class imbalance observed in the dataset. Interestingly, we saw the best performance in the more balanced datasets, more balanced meaning with regards to distribution of coherence labels. There was also evidence to suggest the level of graph connectivity had an impact on performance. However, this varied across datasets and per level of connectivity. This can be seen when we observe disambiguation of difficult labels, but at different levels of connectivity again. So there seems to be something happening to improve performance per graph construction method, maybe a sweet spot of connectivity, but this has to be further investigated since it was so varied per data set. Finally, we found use of the GATT architecture unfeasible, especially given the computing resources. As a result, it was not used in the full study beyond the optimization stage. There was some promising initial results of using GATT architecture, but due to their poor overall performance, further study would be required to come to a definite conclusion. We found that the state-of-the-art GCN architecture performed very well on the EDU data, and due to fewer parameters, was much more computationally efficient. We also tried an implementation of the GATT model, which incorporated edge features, but this significantly slowed computation time, ultimately being unfeasible. Here's just a brief informal comparison of the computation times. So to discuss, the F1 score consideration should be used, but to guide deeper questions into the nature of the methodology, results, and datasets. There appears to be some merit in EDU preprocessing, especially when disambiguating difficult classes, but further work inquiring into the reasons behind this is still required. The best performance datasets were well balanced, giving suggestion for preprocessing methods in future studies. And on to limitations. Although we were able to gain an informed idea through an optimization search, the GATT architecture was largely held back by computational considerations. Secondly, not enough variety in data was used to be able to generalize these findings broadly enough to make any definite conclusions. And finally, we did not use regression metrics to assess results, which would be more useful given the ordered nature of the coherence labels. As such, the potential for deeper insight is somewhat restricted here. So, building off of that, future work should focus on the strengths of GCN architecture, especially given the promising results. We should also consider the use of the test of English as a foreign language dataset, since longer text data is needed, possibly with more structure as well. And this raises the question of what other types of datasets may be helpful for this task. Finally, it would be nice to see how LLMs behave in this task as another perspective for comparison, or as well as for the feature extraction stage of the work. So to conclude, we provided a new method of graph representation of text data using feature extraction, and we identify a more computationally efficient architecture in GCN, or graph convolutional networks, for the given task. And we establish a new benchmark in F1 score justified by the terms of the problem. We do identify potential for GATT architecture to possibly be useful, going off of increased performance with EDU preprocessing, and we provide some legitimization to the process of applying discourse coherence principles in a computational setting. Oh, so quick aside, about a climate impact. I forgot I had that in there. Yeah, so here are my references, and thank you for your attention.
Okay, thank you, Michael, for your presentation. We're now open for questions.
Thanks, Michael. Really interesting topic the approach that you tried in your work. I was wondering, when you come up with the representation, the text being represented as a graph, did you check the topology, the structure of the graph, if it's homogeneous or heterogeneous, in the sense that for some specific, I guess, data sets, the structure will be very much different than other data sets. And the issue is that when you are dealing with graph convolutional networks, for example, the topology of the graph has impact in some of the analysis. So just wondering about this part.
Yes, thank you for your question. So to answer that, no, directly, it was used, topology comparison was used for the previous study, which used graphs constructed with sentence similarities, but I did not do the same. I did not do a similar thing for my study, and that is something that I simply had not considered. So thank you for raising that point, and yeah, I'd be very interested to see where that would lead as well. Thank you.
Hi, Michael. Thanks for your presentation. I was wondering, so you mentioned, if I understood correctly, that you used a state-of-the-art tool to identify the discourse units. And I was wondering, how much do you trust that tool, and if it is possible to use a gold standard? Oh, sorry, no, you cannot use a gold standard. Yeah, so do you think that model, that tool that you use for the discourse units identification, was it good enough? Because I think that's a kind of a quite hard task in the first place. Thank you.
Thank you for your question. No, 100%. I did not go into it with full faith in that there would be zero loss or zero errors carried on, because for both tasks of firstly EDU segmentation and RST parsing, the current state-of-the-art models still uh, have some degree of error, which would be carried on. And I think off the top of my head, the RST parsing models are trained off of I think they're trained off of oh, I think it's a certain type of discourse. It's Wall Street data or something, which was used to provide a gold standard for RST trees. And so even in that, it's quite different from the types of discourse used. So I think for a more holistic and thorough coverage of the problem, it would require much more work in tailoring training data sets specifically related to these types of discourse we're looking at. So to answer your question, I did not go into it having complete faith, but if anything, it was a place to start. So yes, it was something I was constantly thinking about, and with regards to how much time I had available, maybe not now, but certainly going forwards, yes, it would be something worth spending more time on.
Okay, thank you, Michael. And I think we'll move on to the next paper.
Thank you all. Thank you. Have a good day.
The next paper is comparing plausibility estimates in base and instruction-tuned large language models. And this will be presented by Emmanuel, and this is an abstract paper.
Thank you so much. My name is Emanuele, and I'm happy to be presenting here this work on behalf of my co-authors. So, semantic plausibility. There is a strong tradition of psycholinguistic evidence for the existence of a generalized event knowledge in human semantic memory. We know that humans have expectations about verbs and argument combinations depending on the plausibility of the situation described by a sentence. And there are a lot of behavioral effects that have been observed in the psycholinguistic literature, such as shorter reading times and shorter eye fixation durations in eye tracking, while processing plausible sentences compared to implausible ones. Since LLMs are trained via next word prediction on massive text corpora, it is very likely that they also absorb a part of this event knowledge. And how can we evaluate event knowledge in LLMs? A traditional technique is the comparison of minimal sentence pairs that differ by their degree of semantic plausibility. In a first traditional methodology, we extract the log probabilities for the sentences using a language model, and we pick the most likely sentence as the most plausible. In a second method, we directly prompt the LLM for plausibility. Why prompting is so interesting? Because it might help us to filter out some spurious factors that enter into the computation of log probabilities. And moreover, it allows us to test LLMs in a setting similar to humans, like in a question as in a psycholinguistic survey. So these are our research questions. Which method is closer to human performance on semantic plausibility judgments, and how does instruction tuning affect the performance of LLMs? So we run this evaluation via minimal sentence pairs, which means that given a plausible, implausible, transitive sentence pair, we let LLM score each sentence, and we measure the accuracy, the number of times the model assigns a higher score to the plausible sentence. For the datasets, we used two sets of minimal sentence pairs from the previous literature. They come with the human judgments of typicality or plausibility on a scale from 1 not plausible at all to 7 very plausible, for a total of 2,000 pairs. And this is how the items in the dataset look like. I ask you to pay attention specifically to the items in the Fedorenko et al. Dataset, because they can be split in two subsets. In both subsets, the implausible items have been created by swapping the noun phrases corresponding to the agent and the patient of the sentence. But in one subset, both refer to animate entities. So the swap of the noun phrases leads to the creation of an unlikely sentence. In another subset, we have one animate entity and one inanimate entity. So the swap of the noun phrases leads to the violation of the selectional restriction of the verb, and thus the creation of an impossible sentence, such as the laptop bought the teacher. We use, for the large language models, Bayes and instruction-tuned versions of Mistral, Falcon, and MPT, each of them with 7 billion parameters. For the methods, we used log probabilities. We computed the sum of the log probability of each sentence token given the previous context with these autoregressive models. And then we also had different types of prompt to explicitly query the semantic plausibility of a sentence. So here you can see the different prompts that we tried. We adapted them from a previous study from Hu and Levy that was more focusing on syntax. So here we are more interested in the semantic side. And here you have the scores for the log probabilities in the histograms on the left and the best prompting setting on the right. You can see the log probabilities in general, they are more reliable than prompting, which tends to be more like a hit and miss. The only model that is consistently good with prompting is the Mistral model, while Falcon and MPT, they perform close to the chance level. We can also observe on the left that the animate-animate subset of the Fedorenko dataset tends to be more challenging with the models, suggesting that when the models cannot rely on the animacy distinction between the agent and the patient, they struggle much more in identifying the more plausible item. Log probabilities, they perform very highly, and thus we can assume that they encode substantial semantic plausibility knowledge. But we compared the performance of the models with log probabilities with the performance of humans with a dependency test with a Bonferroni correction, and we realized that they still fall short of human performance. Moreover, in all but one instance, the log probabilities of the instruction-tuned models perform worse than the corresponding base model. Here in this plot, we have the specific breakout of the performance with the log probabilities in the histogram on the left and the prompting, the different types of prompt in the histogram on the right. And you can notice by looking at the light blue bar that Mistral is the only model that in the prompting setting achieves a performance comparable to log probabilities. Here we have a comparison between the base and the instruction-tuned model on the different dataset. And you can see that the base model is almost always doing better than the corresponding instruction-tuned one, in some cases even significantly. And finally, we also run a comparison on the basis of the voice of the sentence. And it can be noticed that for some reason, especially with the active voice sentences, when we go from the base model to the corresponding instruction-tuned model, we have a sharp decrease in the performance. So we can conclude that log probabilities for now are still a more reliable measure of semantic plausibility than prompting, and instruction tuning is not helpful to improve alignment with humans, the results being often worse than with the base models. Thank you for your attention, and I'm happy to take any questions.
I will read your paper. Thank you very much. Very interesting, very thorough. Question about the prompting. Can you give us some details about how you designed the prompts, and if you tried to push the prompting approach to perform empirically the best it may?
Well, we readapted the prompts from our previous study, and the idea was to have a setting that was as close as possible to a psycholinguistic survey. So we wanted to test the LLM as a sort of participant to the experiment. So in most of the prompts, you can compare directly the performance with the log probs in terms of accuracy, with the only exception of the scale Likert scoring, because in that case we have to compare the scores. Probably with some soft prompting approaches, the performance can be further improved. And I guess if one tries few-shot learning, this would definitely help to improve the performance of the LLMs. But yeah, we focus just on this prompt settings with some variation on the surface of the prompt, and the results were quite stable.
I was thinking very simply about a few shots, a few examples.
Yeah, I can guess that few shot might be helpful because I recently read some papers with a similar dataset, and few shots generally helps.
Thank you. It's a very interesting study. I got one question. So in this case, you show that adherence and understanding seems to be two different kind of things. And are there any ways that we can actually fine-tune the prompt in some way or decide what to use under different kind of situations?
Yeah, I guess so. I mean, in our work, I think fine-tuning the prompt goes a bit against the goal of the study, because we want to have a setting that is as close the setting that we used with humans for the psycholinguistic experiment. But yeah, as I said, I think there are probably better ways to fine-tune the prompt and having not necessarily a prompt that is interpretable in human language with which you can achieve better scores on these data sets. Yeah. Thanks.
Question too? No? So when these experiments are, the very interesting study, thank you. When these experiments are done with humans, is it the same outcome? So when I think if I get it right, so when the agent is inanimate, they struggle to score the sentence as plausible or not? Is that a correlation?
The animacy distinction, there are some items in which humans struggle as well. So when you have stuff like the quarterback kiss the cheerleader versus the cheerleader kiss the quarterback, actually you don't have a strong distinction between the plausibility of the two sentences. But in this setting, we removed the sentence pairs for which there was not a clear distinction, because we thought if even humans cannot discriminate between plausible and implausible, it's not worth testing the language model when you don't have like a solid ground truth.
Yeah, and that always happen with the agent, or also if you have it in anonymity in the patient. Does it make sense? The question maybe it doesn't.
So when you have the sentence pair where you have the plausible one that is a animate agent and inanimate patient,
Okay.
and the corresponding implausible one where you have like the laptop about the teacher, it is very easy for both the models and the humans to distinguish the degrees of plausibility.
Yeah. Thank you.
Yeah, thank you for your interesting talk. I'm wondering if the length of the sentence matter in this case, because log likelihood is the log likelihood of each word in that sentence. And from my understanding, longer sentence may have a more unstable log likelihood result. And in this case, how did you decide the length of the sentence in your data?
Well, in this case, we have controlled for the length of the sentences, and we also controlled that the length was the same according to the tokenizer of the different model. Because in some cases, the problem with running this psycholinguistic-like setting with LLMs is that the words that have been counted by the psycholinguist while preparing the stimuli are not necessarily equivalent to the tokens that are identified by the tokenizers. But we have controlled them in order to have sentences of same length. Yeah.
Thank you so much.
So,
okay, for the next paper, we have GenABSA-Vec, Generative Aspect-Based Sentiment Feature Vectorization for Document-Level Sentiment Classification by Minkang, and this is a long paper. Yep, that's right.
Good morning, everyone. My presentation title is Generative Aspect-Based Sentiment Feature Vectorization for Document-Level Sentiment Analysis. The presentation consists of these five following sections. First, let's move to the section 1. Document-level sentiment analysis is the most common NLP tasks. The result of the document sentiment analysis can be used as a feature for the different tasks. For example, to the business intelligence domain, the result can be as a feature for the regression calculation in the score prediction scenario. For the recommender system, it can be as a feature for the user's preference modeling. However, now the text representation faces two problems. The one is the high dimensional. Usually, it's the high dimensional vectors. Second is the text representation are difficult to interpret, because now some text representation method is based on the table lookup method, so it's usually hard to interpret. Based on these two problems, now we can see a specific examples. This is a restaurant review. We can see the face was great, grape juice was delicious. The location of the restaurant is easy to find, the staff is friendly. while the music was too noisy in general, like this restaurant. We generated the representation of these sentences by the word-to-vec and the bird-based representation with the default configuration. We can see the first two lines. They have both of the two have the 100. The first one is 100 dimension. The second is 668 dimensions, and we can see it's hard to locate the sentiment signal for the sentiment classification task. The bottom vectors are measured based on the generative aspect about the vectorization representation. We can see it's only 5-dimensional, and each element in the vector is the sentiment score of these 5 aspects. This aspect is included food, size, ambience, location, and drink. So this is the framework of the proposed method. We divided into 2 stages. The first stage is focused on the ALTA quadruple generation. The second stage is focused on the document level sentiment analysis. For the dataset, there's a brief description of the dataset. We sampled 2,040 samples from the Yelp Open Dataset. This dataset was released in the 2022, and we make it a balanced distribution. Next is how we extracted the aspect-based sentiment analysis quadruple. We employed the T5 base model to make it a text-to-text framework. T5 give a new definition of all the NLP tasks. It's just you can make your original review as an input, and the output is the result you want to have. During the T5, we use the full parameter fine-tuning method. The ALTA quadruple is consist of these 4 elements: aspect category, aspect term, opinion term, and the sentiment polarity. The sentiment polarity is generated by the opinion term. Now this is the overall framework for how we can generate the this feature. It's this low dimensional and the explainable feature. First, we using the fusion lexicon to scoring for the opinion term. Opinion term is from the extracted quadruples. After the scoring, we have a optional operation for this score. We generated from the lexicon. After the feature scaling, this is optional operation. After the feature scaling, because we know some aspect term is not appears only once, so we need to do a integration. There has 2 methods: simple mean and the geometric mean. Then at last, we generated this 5 aspect score feature for the document. Now we can introduce this component step by step. The first is the sentiment lexicon fusion. Because of the limited coverage of the single lexicon, so we did a fusion of these 4 lexicons, Affine, so-called, and WKWSCI, and the SentiWordNet. After we fusion these 4 lexicons, the coverage based on the Yelp 2K dataset, the coverage up to 90%. After the feature lexicon, there's feature scaling. Feature scaling is an optional operation. It means in the feature generation, it's not the necessary, but it also have some give us more chance to explain why we should have this step. We can see this example. This example, the stick was epicureal, while the chicken was fully insipid, but the stuff is nice and the juice is great. We found the opinion term for the stuff and juice is very common, but for steak and the food, for steak and the chicken, as both belong to the food. These two opinion terms, it's hard to find the score based on the fusion lexicon. So we adopted a midpoint imputation method in this step, because we have in the last step here, we have mapped all the score of the lexicons into the same score. It means -5 to 5. So we can see here is the fully range from -5 to 5. We're using the midpoint as an imputation method. Even we don't know, or we don't know the score of these two opinion terms, but we have the sentiment polarity. One is positive, one is negative. So based on the sentiment polarity, we give the midpoint. After the midpoint, we still faced another problem. If we want to, just now we have said if the one aspect not appears only once, so we need to do a aggregation. But we found if we want to do a simple mean aggregation, we have found for the just now examples, these two opinion terms assign -3 and 3 to these opinion terms. We use the simple mean method to have the result as 0. The 0 is represented the aspect not mentioned in the review. But in this review, we have see the food aspect was mentioned twice. So it's not available in this for these samples. So we use a feature scaling to map the -5 to 5 to a new range. The new range is from 1 to 11. After the feature scaling, the representation of the text review is these 5-dimensional vectors. After feature scaling is the feature aggregation, because we saw for the aspect which is not appears only once, we need to do a feature aggregation. There are two feature aggregations, simple mean and geometric mean. To the geometric mean, first we should do a calculation following the equation 1. Then we following the equation 2. After the feature generation, we feed to the 3-layer multi-layer perceptual to have the sentiment polarity. During the training stage, the parameter of the NLP will update. The binary cross entropy loss are selected in this NLP. Here is the result table. Based on the generative ALTA features, we compared with the other 4 baselines. The TF-IDF and Word2Vec and BERT we use these 3 methods to generate the text representation. The MLP, we keep the same configuration with the ALTA generative features. The print sentiment, this is a pre-trained sentiment analysis model. Based on this result, we found the ALTA aspect-based sentiment analysis generative features with the geometric mean received a best score for the accuracy precision, recall, and F1 score. So this is two specific samples we selected from the test set. One is the positive, another is the negative. We can see for the positive one, the representation of this text review, food, service, and the ambience has a strong positive sentiment signal, so lead to this document being positive. For the second one, this is negative. This is negative samples. Also, we can see the food, service, and ambience is obvious. The negative samples, sentiment signals also lead to its being a negative document. In the future, they also have limitations. So we want to explore the other domains, like not only focused on the restaurant review, we also can try maybe hotel and other domains. And the second limitation is the limited polarity. We want to contain the neutral polarity. Maybe we can try to the multi-classification in the future. The last one is the limited size of the data set. We can try in the more larger data set. And future work, we also want to fine-tuning more pre-trained language model, not only focused on T5. We also can try another encoder, decoder framework, or only decoder framework. And also we want to try exploring the other imputation method, not focused on just the midpoint. Thank you.
Okay, we're now open for questions. Yep.
Hi, very interesting talk. Thank you. Just wondering, sorry, this is not necessarily a question, but it's just an observation. So you have two different methods to do the mean. One is arithmetic mean and the other one is geometric mean. Sorry, could you go back to that slide? Like, do we know if geometric mean is like consistently performant across the models?
This page.
Oh, sorry, can you go back to the results for the... So I'm just wondering, have you done, sorry, do we know if geometric mean is like consistently performant across different settings, or is it only for this one configuration?
Geometric mean is for the full data set. It's for the data set we used in the experiment.
Also, I'm just wondering, so it seems like geometric mean is better than simple arithmetic mean, but I'm wondering if you have considered doing like a weighted mean.
Not as a weighted mean.
Yeah, but I'm wondering if you have considered it because maybe different features have different weight, and maybe that might improve the.
Geometric mean is only focused on aggregated the one aspect. Maybe because maybe we can see this picture here. For the food aspect, we have much more quadruples extracted from the food. So, but our purpose is want to compress the 5-dimensional vector. So for the food, we only have one element to represent the score of the food. The geometric mean is only works for the compress all the sentiment score of food.
Oh, so only for one aspect. Okay, okay.
One aspect.
Okay.
It want to stand for an overall trend of one aspect.
Yeah, thank you.
Hi, very nice talk. First of all, thank you. The question that I would like to ask is that how did you decide all those 5 features, like food, service, ambience, location, and drink? Like, how are they determined? Because I imagine there could be other features that could be useful for it, like for example, like price, or maybe the type of like whether it's like Japanese food or American food, for example. Like how are they determined?
These four aspects is defined by the Simonds ALTA 2016. Actually, they also have the more details attribute, because first on we also want to consider all the aspect detail, like you say, the food price, food category, or the other attribute. But if we consider all the details attribute in the vector, we will receive the much more missing value, because not all the reviews will mention about the detailed about the food, service, price, and these five aspects. So we just consider the more general aspect in the representation vector. Thank you.
For the next paper, we have MoDEM, Mixture of Domain Expert Models. And the speaker is Toby. This is a long paper.
Thank you. So hi everyone, I'm Toby. I'm an undergraduate researcher at the University of Melbourne. Also, thank you. Also a research fellow at Martian AI. Today I'm going to be talking about my paper, MoDEM, Mixture of Domain Expert Models, which hopefully by the end you get the pun I slipped in there. The paper was in collaboration with Kamal and Jehan, who are also attending the conference. So before we jump into the details of our approach, let's set the scene. So right now we have these models like Qwen 2.5 Maths and DeepSeek Code that are really good at a certain domain. So for example, Qwen 2.5 Maths, the 72 billion parameter model, is actually the state-of-the-art model right now for the maths benchmark. So it has the highest score on the benchmark. And likewise, if you believe the benchmarks, Qwen 2.5 Coda, the 7 billion parameter model, is on par with GPT-4o. So these domain-specific models give us huge performance to cost ratios, because obviously the smaller models are much cheaper to run. The problem inherently, though, is that although these models are really good at their domain, they're not very good at doing things outside of their domain. So for example, Qwen 2.5 Math might be really great at maths, but it's not so great at writing poetry. So we need to find some kind of system to combine these different models together in such a way that we maintain the general performance of the model while also leveraging the domain-specific improvements we get from these models. So yeah, as I just said there. So why is this super important? Well, these models give us a huge cost to performance ratio improvement. The other kind of big thing is like, it may not actually be possible to push the bounds of making one general purpose model for this size. So for example, say Llama 3.1 70 billion, it may not actually be possible to make a general purpose model that can reach the levels of a domain specific model. The analogy I like to use is say we're around, humans, for example. We don't just have like one human who's an expert in everything. We have, well, unless you're like John von Neumann, but we instead have different experts at different things, and we delegate tasks to the correct expert in that given field. Kind of a key point here, and something that's really important in modern research, is that sparsity is key. You don't really want, like, say you have massive model like Llama 4 or 5 billion. A bunch of things are going on in there that are kind of not really super useful for your exact prompt. So say, there might be a part of the model that's doing some grammar stuff and you've got a maths prompt. It's kind of useless to run those parameters. So we're wasting a whole bunch of compute on that. So before we jump into our work, we're going to just talk about some of the related work. The most common of which is the sparse transformer. This is like the traditional mixture of experts. Essentially how this works is inside of each transformer block, there's a router. And basically, depending on the residual stream, which is determined by the prompt, a different feed-forward network is activated. So kind of the idea is, say we're asking a maths problem. The hope is that like some of the feed-forward networks is doing something maths-related, and some of the other feed-forward networks are doing some of the grammar. Kind of the fundamental issue here, though, is one, it's super unstable to train models like this. So if one feed-forward network gets better than the other feed-forward networks, you're always just going to route to that feed-forward network inside each transformer block. There's all kinds of other issues too with like, you can't really just like take it off the shelf model and apply this to it. Kind of the other big issue is you don't get the clear domain specialization. So you don't just get like one feed-forward network that's like, this is a maths one. You actually get like really complicated ones where it's like, this one's doing a comma, and it's not really doing like the high-level abstraction that we're looking for. The other approach is the end-to-end MOE. So essentially what this is we're training the model and the routers at one time. So it's end-to-end, everything's getting trained at the same time. Now, off the record, there's a lot of leaks that GPT-4 is trained this way with 12 70 billion parameter models. But again, it's got a similar issue, right? If one model gets better than the rest of the models, the router is just going to learn to always route it to the model that's the best, because you're going to get the lowest loss from doing that. So it's kind of it causes very unstable training dynamics. The other thing too is if I want to switch out one of the models, I have to retrain my router, which is very annoying. Kind of the last approach that's currently out there is called model routing. And essentially what this is you try and predict the performance of a model before it actually does the inference. So how this works is, say you got two models, you got a Llama 7 billion and you got GPT-4o. You're trying to predict, say I give you a prompt, how many R's are in strawberry, everyone's favorite. It's very hard to know beforehand how these models are going to perform on that given question. Like I don't know if to fix the problem with Llama 7 billion not being able to answer that problem. So the problem is it's a super messy classification problem. It's not a very rich source. So you actually see that we get performance that's barely better than just randomly routing between the two different models. So our approach is called MoDEM. And essentially what we do is we take a prompt and we classify it by the domain. And then we assign a model for that specific domain. So for example, we get a prompt that's something like, prove that the square root 2 is irrational. Our router would then classify that as a maths problem and then route it to our maths expert that we assign. So in our case, that would be Quen 2.5 math, for example. The big advantage of our approach is one, the routing of just classifying a domain is a way, way cleaner routing classification problem. So you get way higher accuracy. Other big thing is you can easily switch out the experts here. So say, tomorrow Quen 3 drops their new maths model. We can easily just pop that into our network. We don't have to retrain the whole thing end to end. It also makes it really easy to integrate different models from different sources. So say we might have models from DeepSeek, or we might have models from Quen, and we might have models from ChatGPT, from OpenAI, for example. So just getting into some of the logistics. For our router, we use just a classic Didar router. Tried a few different ones. They all work pretty well. It's just a pretty basic Didar. There's some calculus around surrounding like how many parameters you spend on the routing as opposed to the actual inference. You don't want to obviously spend a whole bunch of, you don't want to spend 10 billion parameters on the routing and then 7 billion on the inference, because that calculus doesn't make much sense. You may as well just spend the extra parameters on the actual inference. So we reached, I think, a good balance there with only about 0.42% of the parameters being used for the actual routing. So for the training data, essentially, it's a bit problematic, right? Like, how do you get clear prompts that are in a certain domain? So say we need a bunch of prompt examples of health-related questions. So essentially, we just scrape Hugging Face. I just searched through by hand a bunch of these kind of domain-specific data sets. I think a big thing that's very underutilized in academia that's used a lot in industry is synthetic data generation. It's so cheap nowadays to generate this data. Like for GPT-4o, it's like, 30 cents for 1 million tokens. So you can actually just super cheaply generate a bunch of these example data and use it for your training your classifiers. The problem we had with our Hugging Face data sets is we lack kind of conversational style problems. And that's something synthetic data really helped us with. So for the test data, we use MLU. We didn't train on the training set of that. So MLU is really nice because it has clear classifications into different domains. Kind of an issue is there's always some ambiguity surrounding what domain something is. So example, this here, like, is that a health question or is that a science question or is that a history question? Who knows? So it's kind of a bit ambiguous, right? So overall, we saw really great performance, especially on things like math. There is some lower performance on things like other, but that's just because of the ambiguity. I tested out by hand, and I think about 85 to 86% is kind of like the cap of what you can do because there's just so much ambiguity around the domains. So yeah, overall, we achieved really great performance. So, essentially, what we saw was great performance on these test style ones. There's still a little bit more to be done around like conversational style questions, which is just a matter of generating more synthetic data. So for the actual experts we selected, we first of all, we made two different configurations. We did a small one with all the experts being less than 8 billion parameters, and a medium one with all the experts being less than 73 billion parameters. So essentially we just kind of looked at the benchmarks and we just picked whichever models were the best for those benchmarks. So you can see we use Quen 2.5 math, as I've mentioned a lot throughout this talk. But yeah. A small point that I think is underappreciated is that it's super easy to fine-tune these models. Post-training is really cost-efficient. So for around $100, you can actually fine-tune Llama 3 8 billion to be as performant as GPT-4 or mass instruct. Like, it's incredible how cheap it is to do post-training. But yeah, just a side point on how easy it is to make these experts. So our results. So in the green is our performance. We're comparing it to Llama 3.1 8 billion because that's kind of considered state-of-the-art for the given size. You can see across the board we outperform it. It's particularly in domain-specific benchmarks like math and GSM-8K, we get significantly performance improvements. But the really surprising thing and great sign is that even in general purpose benchmarks like MLU and GPQA, we still see performance improvements. Likewise, in our medium MoDEM, we see very similar results. So again, we outperform them all across the board, and still see performance improvements even in the general benchmarks like MLU and GPQA. A really big point of our research as a whole was we reached state-of-the-art cost efficiency for our given model size. So even on MLU, which if we go back, was one of our least improved benchmarks, we still reached state-of-the-art performance for the cost to performance on MLU. So what does this mean? Well, one, as I've said a few times, we've reached state-of-the-art performance at the price level. So I think this is a really good sign for architectures like this. You need some kind of sparsity in order to get this kind of cost to performance ratio. It's kind of hard for these general models like Llama 3.1, 72 billion or whatever to compete against these sparse models. A really big kind of small thing, especially in industry, is we can't really scale the compute we put into these big models anymore. It's a big problem why we've kind of plateaued at GPT-4. We can't actually get any more compute into these models. So a really big advantage of an architecture like this is that you can train the models separately and put them all together at the end. So we don't have to worry about multi-data center training or any of that, distributed system shenanigans. We can just train these models separately and then bring them all together. Likewise, that also means that we can use models from different suppliers, so Qwen 2.5 or DeepSeek or whoever your favorite LLM provider is. I think another really good point is, say your model, right, it's bad at maths, for example. When you have a general purpose model, that means you have to retrain the whole model. But in our architecture, you can just retrain the math part, the math expert, and just train that and do your post-training or whatever on that, instead of having to retrain the whole model. So it makes it much, much cheaper to improve performance on certain domains. Kind of a small point, but it's really important. If you actually read these papers like DeepSeek, even like code and math, they have fundamentally different post-training techniques for different models, depending on the domain. So for example, in math, everyone's using PPO with star-based methods because it's very easy to validate. And the coding stuff is really just about take a bunch of GitHub code and how do we put this in some instruction setting where it's like a question and it's generated code. So depending on the domain, we have different post-training techniques. And so when you have a general purpose model, you can't do that because it's one model. You can't separate the post-training depending on the domain. But when you have domain experts, you can do that. So just small thing, the future potential. Right now, there isn't a huge amount of these domain-specific models. Actually, since the paper came out, Mistral has released something very similar saying that this kind of architecture is going to be the future and they're going to be releasing a bunch of domain expert models. But essentially, when more of these models start coming out, we're just going to see more and more performance improvements over our baseline, which are the general purpose models. And yeah, so future work, there is still a little bit to be done about the actual router. We didn't explore too much different techniques, but there is still a little bit to be done about making that a general purpose. I think BERT routers are the best way to go about that, but there is still some optimization about making it more general purpose. And yeah, I think that's the end of my talk.
Hi. Really good point about the price and also the just the management as well of retraining for different domains. At what point do you anticipate the number of domains is going to turn that around? Because you could have a really large number of domains. You can also have hierarchy of domains and subdomains. And at some point, that's going to end up costing you more, particularly with your routing getting very complex, than having, I think you've got how many domains? 7 or 8? 5, yep. Cool. Thank you.
Really good question. So first thing, it depends on the size of the model. So for smaller models, you can have a bunch of these different domain experts. A really kind of clear improvement for this is to have a different router that's the difficulty of the question. So say if it's a hard math question, we should send to a small model, or we send to a medium model or a hard model. It's a very good e-research question, and it's going to be hard to measure what is the calculus about the number of models as opposed to the size of them. Again, you see some improvements when you fine-tune, say, a 7 billion parameter model, it's hard to get certain reasoning abilities that a 70 billion parameter model has. You just can't get, you don't get the kind of general reasoning you get out of a 7 billion parameter model that you get out of 70. So although say mass instruct, right, we demonstrated that we can get performance improvements. Maybe you could just have an expert for every single benchmark and you could choose the benchmarks and get a 7 billion parameter model with GPT-4o. So, I mean, you could do that, but I don't know how well that would work in actual application. Yeah. Is there any other questions or? Perfect. Oh, one more, sorry.
Thank you. Super interesting, actually. It's powerful, and also it's nice that it's like interpretable. Do you still see cases where we might see like a really large general purpose model? Like, you know, you mentioned this example query that really doesn't like is ambiguous. Is it for these kind of cases, or are you just gonna have a fallback model that is like every other query falls there?
Yeah, so really great question. So very off the record, because of NDAs, you should train a really big model to start with and then do distillation to make these experts. So how GPT-4 works, the leaks on Twitter, it was like a 1.2 trillion parameter model, and then they did distillation to train GPT-4o. So the real big advantage, like when you make a general purpose model, you can get performance that you can't get out of these smaller models, but it's way, way too expensive to run in production. So the purpose of these general purpose models is to create data to distill to train these smaller experts. Does that kind of make sense? Yeah, perfect. Thanks. Yeah. Cheers. Oh, sorry. One more.
Hi. So I'm aware that like, so when you do routing, you pick one specific domain, and I understand that because you evaluate on MMLU, this would probably work in most cases. I'm just like thinking about like some edge cases. For example, when you have a multi-domain problem. Like, for example, if you have a problem that involves maybe like some advanced math and health at the same time, then have you considered maybe like how to go about it?
Yeah, that's a really good question. So if you read some of the modern like mixture of expert models, they'll use multiple models at a time, and then they'll like combine them together. So I think there's a really interesting point about like how do we actually combine these two like different models together in the actual output. So like say it's a kind of a cross domain, it's a science and a maths question. Could we actually get both of these models to work at the same time instead of just routing it to one or the other? But I find like, I didn't really clarify this in the paper, but other is like general. So like if it is completely outside of these domains, it just gets routed to the general one. But you find that like, although these models like are domain specialized, they are not horrible at things adjacent to it. So say it's a math problem, like Quen 2.5 math can still do science problems pretty well. So they're not like super duper hyper specialized, but yeah, it's a really good question. Thanks so much.
Okay, next paper is Advancing Community Directories, Leveraging Large Language Models for Automated Extraction and MARC Standard Venue Availability Notes. The presenter is Mostafa, and this is a long paper.
Thank you. Hello, everyone. I'm Mostafa Didar from Adelaide Uni. And this was part of my industry project for my master's in AI and machine learning degree in partnership with SA Community. And my supervisors are Dr. Tushari Atapattu and Dr. Minasha Tilakaratne. And my industry supervisor is Catherine McIntyre. So I'll start with SA Community. SA Community is a free online community information service supported by the government of South Australia. And they're just an online directory of all the organizations in South Australia. And this is the problem statement which we tried to tackle. So our focus was to transform unstructured text of community service information into specific data elements, making that information more amenable to MARC standards. I'll talk more about MARC later on, but let's talk about the scope. So we primarily focused on meeting rooms and facilities available, which we refer to as venue availability here. And the relevance of the study is that it had high demand as indicated by Google Analytics searches on the SA community directory. So the main research question is how can we improve data management practices, accessibility, and enhance decision-making process within community and event management sectors? So what is MARC? So MARC is a machine-readable cataloging standard by the Library of Congress, and it is widely adopted everywhere. And for our purpose, we used MARC as a standard, as it was a requirement for the project. So the data was divided into two different databases. One was the CVCRM database of essay community, and the other was a subject database, and which had more than like 14,000 organizations all over South Australia, including not-for-profits, private organizations, and government organizations. And the subjects that are covered are like sports, arts, recreation, health, welfare, housing, education. And these are all freely available to download at data.gov, and you can also check out the essay community directory. So we followed a 5-step development process, starting from data collection and annotation, data pre-processing, feature extraction, model development, and inference and testing. So yeah, the essay community database contains a comprehensive report of all organizations, their names, addresses, contact details, website information, etc. And the subject database contains subjects, which we'll get into on the next slide. So there were lots of columns, but we were particularly interested in these columns exactly, which are organization names, IDs, subject IDs, venue hire information, which is an open text field, comments, again, which is an open text field, services, and subject, which are all open text fields, and they're unstructured. And the subjects we were interested were subjects related to venue hires, organizations that have venue hiring capability, halls for hire, community facilities, convention facilities, conference venues, meeting rooms, clubs, groups, etc. So to combine both the databases, we just performed an inner join of using subject ID. We conducted some exploratory data analysis to see how or what are the most frequently occurring words within the columns. Here we can see the word cloud for venue hire column, the word cloud for services column, and the word cloud for comments column. And we then moved onto data pre-processing techniques, where we removed HTML tags, removed unnecessary white spaces and punctuations, lowercase the text, got rid of organizations that don't have a venue hire, and we annotated a subset of the final cleaned data set. We used an open source tool called data annotation tool called Docano. Docano handles JSON-L files, and JSON-L is a different format to JSON, which is delimited by just lines instead of tabs. And these are the entities that we extracted, or we were looking to extract, according to MARC standards. So general description of facilities, names and location, physical description, capacity, equipment available, rental fees, special restrictions, etc. And here's just a snapshot of the Docano platform, where you can see entities marked in different colors. And there are some nested entities as well. So one reason we needed to perform IOB tagging was because transformer models, they get confused when they just see labeled data. So IOB tagging essentially helps us mark the beginning, inside and outside boundaries within the texts, and which actually helps the transformer model actually pick up entities, especially in sequence labeling tasks, such as our task, which is named entity recognition. So we use these tools, Hugging Face for the Roberta model, PyTorch to implement the model, to log and monitor the model. We used weights and biases. And here's a picture of BERT. And that's the overall system overview of our project, where you can see the user inputs a text entry. It goes through a pre-processing pipeline. goes through the Roberta model and predicts the IOB tags, outputs the prediction, does some semantic chunking, and then calculates metrics like accuracy, precision, recall, and F1 scores, and then feeds it back to the user. And as you know, Roberta is a transformer model made by Facebook AI. It is an optimized, robustly optimized version of BERT, and the input text is fed into the tokenizer layer, and then there's a classification layer, and then and it's embedded into vector embeddings, and then again it's classified using the last classification layer, and the prediction is span out. After lots of tweaking with the hyperparameters, these were the most optimum hyperparameters which we could come up with. And yeah, batch size of 16, 50 epochs, we ran it for 50 epochs and train it for 50 epochs and considered a cosine warm-up scheduler. And here are some of the results for our training set, which we can see a graph of training versus loss and learning rate. The graph starts and there's a smooth downward trend which indicates good learning, and it follows a typical warm-up and decay pattern and gradually decreases, which is good in our case. For the gradient normalization, we could see some fluctuations and overall instability, but overall it wasn't bad, and we will cover some of it in the next few slides. And for the validation set, we could see the evaluation accuracy improves consistently across all epochs, and the evaluation loss starts high, but decreases to 1.2%, indicates good learning process. The precision and recall shows more stability, shows stable results, but recall is a bit more stable than precision here. And on the validation set, the F1 score has a big performance of around 60%, shows fluctuations, but overall upward trend. And we logged all of these results using weights and biases. And these are all the experimentations across different days during the project. And here we can see the accuracy and loss scores. And here we can see the test set recall and precision scores. Here we can see the F1 scores. And this is just some more comparison on the evaluation sets results. We also implemented a technique called active learning, where after each model training session, we then manually label a subset of the predictions which have a probability distribution and a probability class of less than a given threshold. So we start with a small label data set, use the model to predict on the unlabeled data, identify and label the most uncertain predictions, and then retail the model with new annotations. So the benefits of using active learning is it reduces annotation effort by prioritizing impactful samples, and it has actually achieved a steady improvement in model performance and increased our results from around 68% to 75% on the latest iteration. So here's some key observations. We could see that the model improved overall across epochs. It had a constant learning, training loss constantly decreased, while evaluation and test metrics improved. There were some gaps between training and evaluation loss, which suggests potential overfitting, which we could address in future iterations. And balanced performance and F1 scores around 0.75 indicates a balanced model performance. Why we chose Roberta and we didn't go with other open source, other closed source large language models, because Roberta is open source and it allows for extensive customization to meet our specific project requirement. And it's cost effective. We don't have we don't have a recurring API usage fees, and local deployment reduces operational costs. Ideal for resource-limited projects such as ours, where we had like resource constraints and budget constraints. And the data remains on the local infrastructure, mitigating privacy concerns, and it avoids external data sharing. And task-specific performance, because we could fine-tune the model to for our specific task, and it tailored it to the community management needs, which outperform generalized closed source models in precision and recall. And it has a good community support as well, and we had and it has extensive documentations and tools to make the implementation straightforward. So there are some of the implications of the project where the project resulted in improving data standardization, interoperability improved search and retrieval, improved for specific venue hire searches on Google. It saves time, and then the data can be transferred through APIs consistently across different platforms, and it can be easily integrated with other services as well. Some recommendations, we could consider further fine-tuning and further hyperparameter tuning to improve the F1 scores and reduce overfitting, explore data augmentation techniques to improve model generalization, experiment with different pre-trained models or custom architectures to improve the performance, and we could try stronger regularization techniques to prevent overfitting. So we made sure we were very careful while handling the data of organizations in South Australia. So we anonymized personal data to ensure confidentiality. We conducted regular evaluations to identify and correct model biases. We adhered to ethical guidelines and data sharing agreements, and we were very clear on documenting the whole process and practiced best methodologies for stakeholder trust. And that was my project. Thank you. If you have any questions, I'm open to answering them. Thank you so much.
Time for 2 questions.
Yes.
So thank you for the presentation. Based on what you have over here, it seems like you did a pretty extensive data cleaning process, and later on aligned it to the MARC compliance kind of venue kind of data format. The thing that I find interesting is that you trained the Roberta model for about 50 epochs, and it actually converges relatively quickly. However, at the very end, when you use active learning, you actually see that the F1 score went from around 60% up to 75%. Did you do a qualitative analysis to look at what kind of things are causing the performance improvements? Is it because that the data set itself is imbalanced, or is there other reasons that is causing this kind of change in performance?
So yeah, one of the reasons was the data set was imbalanced when we first had it, and we had to go through an extensive cleaning process and labeling process. So once we ran it through an active learning loop, and then we could be more sure of what labels and be more sure of the data labels. So that actually improved the prediction F1 scores. And I did not look into generalization or other techniques, but yeah, the data quality definitely improved after each active learning cycle. Any other questions? Yes.
Thanks. So putting aside the methodology, the approach that you have explained in detail, and thanks for that, I was just wondering, because the main task is the summarization, right? And name entity recognition. So, but have you, like the let's say the output is being used and currently, and who is using it?
Yes, thank you for your question. So currently, SA community is using their output for their community directory, and so we ran the algorithm, the model, and then we came up with the output and we provided it to them. And so it's on their website now. And so when organizations sign up to the SA community directory, each organization has a venue. So this was something they were looking at because as seen on Google Analytics, lots of people were searching for like venue hiring capabilities in organizations, but they were getting confused for South Australia. So this research and this results would definitely help, people look for venue hiring capabilities and organizations that actually provide venue hiring capabilities. Thank you.
Okay, thank you very much.